Ms. Myers.
Let me inspire you.
This is about.
We're going to look at drawing ionic and covalent bonds. Before we begin, let's review a few things. Valence electrons are those located in the outermost shell of an atom. And remember, the group number is what tells you how many valence electrons there are. The elements in group 18, so that's on the far right, they have enough valence electrons to fill their outer shells. So if no electrons are needed, the atom is stable and it does not need to bond. All other elements will need 8 valence electrons to be stable, except for hydrogen. It needs 2 because the first energy level or shell is stable with 2. Ionic bonds are bonds between a metal and a nonmetal, and then covalent bonds are those between 2 or more nonmetals. So that's it for the review. Let's get started. Remember, the goal is to have 8 electrons, which creates a full outer shell, except for hydrogen because it is stable with 2 electrons. Because atoms want to be stable, they will behave in a way that will get them enough electrons to be stable. This is where and why bonding happens. If you think of it like a parking lot, if the parking lot charges to park per day, then it's most happy if it is full. An atom's parking lot can hold 8 cars, which really means it can hold 8 electrons. So that's its mission when bonding, to find another atom that can give it 8. But remember, hydrogen only needs 2. When bonding occurs, atoms will lose, gain, or share electrons. In ionic bonds, atoms lose or gain electrons. If an atom loses or gains electrons, it's going to have a charge. So these are called ions. If they lose electrons, then the charge is positive. And if they gain electrons, then the charge is negative. Now consider this. Is it easier to move 1 car to another parking lot or to move 7? It's easier to move 1. When it comes to ionic bonding, that's bonding between metals and nonmetals, it is the same. So it takes less energy and less work for an atom to move 1 electron than to move 7. They're quite lazy. So therefore, atoms that have fewer valence electrons are going to lose them, and atoms with more valence electrons will gain them. So those are the lazy ones. If you remember the periodic table patterns and valence electrons, group 1 is 1, 2 is 2, skip the middle, and then 13 is 3, 14 is 4, etc. And so don't forget that. We're not going to worry about group 18 because those don't really like to bond. Metals are located on the left side of the zigzag line. So notice those have a lesser amount of valence electrons if group 1 is 1, 2 is 2, and so forth. This means that metals will lose electrons and nonmetals will gain electrons because they have more to move, and again, they're lazy. They don't want to move those. It takes too much energy, too much work. Side note, in chemical formulas, metals are always written first. We'll see that in a little bit. So when sodium loses an electron, it loses negativity, becoming positive because it lost electrons and they're negative. If you think of it like this, if you have a phone that is broken and you sell it, well then you are happy or positive because you lost the problem, which is the electron. You lost negativity, and this is the same with electrons. When an atom loses electrons, it loses negativity, becoming positive, giving it a positive charge. So when chlorine gains an electron, it gains negativity, becoming negative overall for that atom. So the other side of the deal with the phone, the person that buys the broken phone isn't too happy. They gained a problem, electron, gaining negativity. This is how it works with electrons. When an atom gains electrons, it's gaining negativity, giving it a negative charge. So these charges are shown in what is called a superscript, also known as an oxidation number. One atom will have a positive charge and one will have a negative charge. So if you think of superscript, think of Superman, superscript, it flies high, it's at the top. A submarine, which is a subscript, like H2O, the 2 is a subscript, that's at the bottom. So they're two different things. Make sure you remember that. As you can see with these examples, sodium, Na, is a 1 plus charge. Positive ion, which is what that is called a cation. Okay, so if you see that word, it's talking about the positive one. And then on the other side, you have chlorine, which is a charge or oxidation number of 1 minus. It is the negative one, and it's an anion. So sodium in this case is the cation, and chlorine is your anion. This is an example between lithium and fluorine. You'll write out the symbols, and then you look at the valence electrons and make the electron dot diagrams. So lithium is in group 1, it has 1 valence electron. Fluorine is in 17, so it has 7. Then you will show the transfer of the electron, and so fluorine needs 1, lithium has 1 to give, so it works out perfectly. Then on the other side, you will write out the metal first. It's the one that gave away electrons. It's the positive one, so that's a lithium. And then you have fluorine, and fluorine has a 1 minus charge because it gained negativity, becoming negative by 1.
Another one.
So here we have another ionic bond to draw. It's between iodine and magnesium. This one will be a little bit different, so pay close attention to what happens with this one. Okay, so again, first you write out the symbols, and then look at the periodic table to figure out valence electrons. Magnesium will have 2. Iodine has 7 because it's in 17. Now, with this one, iodine only needs 1, and so magnesium can give 1, but the rule is if you get rid of 1, you must get rid of them all. And so to do that with this type of bond, you have to add another iodine. So you'll add another one, and it also has 7 valence electrons, and then you're able to give away the remaining electron magnesium is holding. With the next part, you will write the metal first. It's magnesium. It's the one that gave away or lost electrons. Then you write the nonmetal. Now, for magnesium, it gave away 2, so it lost negativity, becoming positive by 2. Then for iodine, you look at just one of them, and so for only one iodine, it gained an electron, gaining negativity, becoming negative by 1. To show you why we only look at one, we're going to do the crisscross method. And so you write, you have your magnesium and your iodine, the 2 plus and the 1 minus, to write the actual chemical formula, because that is not, we don't say H1 plus O2 minus. We don't say that. We say H2O. And so that's the chemical formula. To write that from this, you will crisscross. So you drop down the 2, we drop the charge off. Put the 2 down by iodine, and then 1 goes by magnesium. You write it out with just the symbols and the numbers at the bottom, the subscripts, and then check it. 1 magnesium, 2 iodines. We have 2 iodines in the problem. Now, remember, it takes a lot of energy for an atom to lose electrons. So those with more valence electrons will behave differently than those with fewer. These are the nonmetals, the ones that have more. In covalent bonds, atoms share electrons. So covalent bonds are between nonmetals. This is like 2 parking lots preferring to combine and make 1 parking lot that will share the profits and the problems. In covalent bonds, charges do not result. There will not be any charges because electrons are shared instead of transferred. And the resulting compound is called a molecule. That's another little review for you. Now we're going to look at drawing covalent bonds. Don't forget ionic, but this is covalent. This is going to be different. Don't confuse the two. Covalent bonds happen between one or more nonmetals. A nonmetal can bond with itself, like you see in this example. Here we have H2, which is hydrogen gas. It's going to be H plus H. For the second one, it's going to be a little bit different, so we can know the difference between the two when we draw the finished part. I have it in a different color, and also the valence electrons are going to be shown as an X for that one. You'll see why. So that's all you do there. You don't draw arrows. And for the final part, you draw both H's, and they each need 2 to be stable. And so in the middle, they're going to each share one with the other. And you see the first one stable with 2, the second one stable with 2, and that's it. So these, I like to say they go to therapy and share their problems in sharing circles. So they're going to bring all the issues to the table and share. That's covalent. This next one is N2, nitrogen gas. It also bonds with itself. Again, you write out the symbols, N plus N, and then it has 5 valence electrons. So each one has 5 valence electrons. I show the second one with X's to show that it's different than the first one with the dots. Now, remember, no transfer, no arrows drawn to show that things moved, because they don't. But in the final part, you need to figure out how many they need to share in between them. If it has 5, each needs 3 more. And so if I put 3 in the middle for the first one and 3 in the middle for the second one, and then the remaining ones on the tops and bottoms, I can have a stable nitrogen with 8 on each side. Okay, so I know in the past we didn't do more than 2, but here you have to do 3 pairs to give each one 8. The last example I'm going to show you is a covalent bond that has different atoms in it. And so this is methane. It's CH4. There's 1 carbon and 4 hydrogens. So when you're doing this, you'll write them out. There's only 1 carbon, but you have to write out all 4 H's. And you determine how many valence electrons there are for each. Hydrogens in group 1, they each have 1 valence electron. And carbon is in 14, and so it will have 4. Again, with the dots and the X's, it's easy to see which electrons belong to which. Now for these, when you're writing out the answer, it's best to put the one that's different in the center. It makes it much easier. So you'll write out carbon, put the 4 valence electrons around it, and then you have the 4 hydrogens. Carbon needs 4 more, each hydrogen needs 1, and so they're going to share 2 between them on each side of carbon. Hydrogen stable with 2, this one's stable with 2, this one's stable with 2, your last one's stable with 2, and then carbon is stable with 8 valence electrons. And so that's what the bond looks like. That's what I want you to do on the test.
Oh yeah, that's about it.